In this question we need to complete the square, so we will first of all need to take out the 9 from everything to give us 9, then brackets x squared minus 6 over 9. 6 over 9 is 2/3 x. Now you don't really need to take it out of the plus 6. You can do, but you don't have to. So now we have a 1x squared here. We're able to complete the square. Ignore the 9, ignore the plus 6. We just want to complete the square for what's in this bracket. So that will give us x. We have to halve the coefficient of x. So half of 2/3 is 1/3. And we then have to square minus 1/3 and subtract it. So square it to give us 1/9 and subtract it to give us that. We can then multiply this out, so that's 9x minus 1/3 all squared minus 1 plus 6, which gives us 9x minus 1/3 squared plus 5. Now, as you can see, this isn't quite in this form yet, so we want to write 9 as 3 squared which looks like this, and since we're squaring this and we're squaring this, we can now write this as 3x minus 1/3 all squared plus 5. This is a bit like the reverse of what you do when you're doing the binomial expansion, because this, if I move this over to here now, this becomes 3x minus 1 squared plus 5. There might be quicker ways to do this, but that's the way I would do it. This is going to help us with part 2. From this we can see the minimum point is 1/3 5. Now if we were to sketch this graph, if I just do a quick sketch here, it would give us a graph a bit like this, where the x value is 1/3 and the y value is 5 here at that minimum point. Now the question is saying, state the smallest value of p for which this is a 1-to-1 function. So x has to be greater than p for it to be a 1-to-1 function. Now a 1-to-1 function means that for every one x value there is only one y value, and vice versa. Now at the moment there isn't, because this one y value up here, this one y value has got 2 x values here and here. So we want to restrict the domain of the quadratic, so it's a 1-to-1 function. Now the way we could do that is to kind of chop the quadratic in half. If I just get rid of what I've just drawn there, if we chop the quadratic in half, in other words, if we get rid of let's just scribble it out. If we get rid of all of this and we just have the quadratic for x values greater than 1/3, then we can see the graph is now a 1-to-1 function. For every one x value there's one y value, and vice versa. So in other words, we have made the domain x is greater than or equal to 1/3, and the graph is now a one-to-one function. So the question is p equals 1/3 would be the smallest value of p to make it a one-to-one function. Now, part 3. In this question, we have to find the inverse function. So fx is 3x minus 1 squared plus 5. To find the inverse, I would call this y, and then I like to swap the x's and the y's round, and rearrange it to get y on its own. This would be x minus 5 equals 3y minus 1 all squared. We should plus or minus the square root of that. X minus 5, that will be 3y minus 1. If we then move over to here, that will give us 3y equals 1 plus or minus the square root of x minus 5. So y is 1/3 plus or minus the square root of x minus 5 over 3. So the inverse function is this. Whoops. Minus 5 over 3. Now, at this point, it's worth checking the domain and range. So the domain of fx is this. The range of fx, well, you can see the range of the y values, so it's always got to be greater than 5 here, the y values. So this is the range of fx. This is the domain. I'll just write range here and domain here. Now, that means that the range of our inverse function is going to be the same as the domain of our original function. Okay, so it might be helpful to write this over here, that for our inverse function, the range is the same as the domain of the original function. So the range of our inverse function is going to be greater than or equal to 1/3, and the domain of our inverse function is going to be the same as the range of the original function. In other words, x is greater than or equal to 5. Now that affects our answer down here, because we know that the range has to be greater than or equal to 1/3, which means we can get rid of that because it can't be less than 1/3. So this is our inverse function here, and the question also asks for the domain of our inverse function. Well, we've worked it out over here that the domain is this, so we can write that down here. For the final part, I've gone back to the original graph, cleared everything up a bit, because the question says what values of q does fx equal q have no solutions. Well, if y equals q, let's say q was 6, for example. If q equals 6, then, whoops, that wasn't great. Let's try again. That's better. So if Q equals 6, for example, there would be 2 solutions here and here. If Q equaled 5, whoops, let's pretend that's a tangent at the bottom there. If Q equaled 5, there would be 1 solution down here. And so you can see that if Q is anything less than 5, there will be no solutions, which is what the question is asking. So Q is less than 5.